Okay, so week eight, first lecture of week eight. This is lecture 15 of the class. Let me just quickly go over what we did last time, at least at the last half of the class. So what we started doing was a renormalization group for the two-dimensional Ising model. And we chose to do a real space renormalization group, which is conceptually very simple, very close to relate to what we already saw in the Kazanov block spin picture. And now we're busy working our way through the calculation. So what we did, we start off with our picture of a set of spins, Ising nearest neighbor spins in principle in an external magnetic field on a triangular lattice. And over here on the right-hand side, I've drawn you a little picture of that triangular lattice. And in a minute, we'll talk about these two particular block spins labeled capital I and capital J in just a minute. We defined the block spin to just add up all the microscopic spins within each block and then take the sign of that. So you can only get a number which is either positive or negative. If it's positive, then you get +1. If it's negative, you get -1. And so that's how we defined our block spin. We can see from the way that we've defined it that the block spin lattice is larger from the original lattice by a factor of the square root of 3. And so then what we decided to do was to work backwards from Onsager's exact solution to work out if we were able to do an exact renormalization group, what renormalization group eigenvalues would we get? And Onsager, in an external magnetic field set equal to 0, calculated what the critical exponents are, and they're shown here on the left-hand panel. And from those numbers, we were able to work through our renormalization group transformation and work out what values we ought to get for the critical exponents summarized by the renormalization group eigenvalue exponent y sub t and the renormalization group eigenvalue exponent y sub h. And those numbers are there on the left-hand page. So those are what we should get if we did it exactly. And now we're going to see how close we get by doing an approximation. So what is the approximation? So the first thing is we said what we're going to do is we're going to imagine that we split up the Hamiltonian into two parts. So look over here on the right-hand side. On the right-hand side, we have a Hamiltonian H naught, which describes the interactions between spins in the same block. And then we have a perturbation V, which describes interactions between spins on different blocks. And you can see in this picture here, I've shown you with the dashed lines, what are the V interactions, and I've shown you what are the interactions within the block H naught. Okay, so that is the setup. I called the microscopic spins within each block as sigma I, and then what we did was we enumerated all the configurations of the microscopic spins for each value of the block spin. So on the left-hand side, if the block spin has value +1, then the configurations of the microscopic spins that can give rise to that, there's 4 such configurations, and they're enumerated on the left-hand panel. Similarly, if I look at the macroscopic configuration, the block spin is -1, then the microscopic configurations that correspond to that are shown below that. And then what we did was we said, well, let's now calculate the effective Hamiltonian, the block spin Hamiltonian. So now we know how that's defined. So on the left-hand panel, we can see that is defined at the top of the page. The effective Hamiltonian, depending on the block spin variables SI, is the original Hamiltonian, e to the Hamiltonian, the Boltzmann factor, and then we sum over the microscopic degrees of freedom, the microscopic spins sigma I, and only include those values which are the ones that are consistent with the desired value of SI. So if you say a block spin has a value +1, then you have to sum over these four configurations that I've indicated on the left-hand side. And so that way we can do the calculation. So we take our Hamiltonian with interactions within a block, the interactions between blocks, and then we want to calculate what is the partition function. And so to compute the partition function, what I defined was an expectation value, the unperturbed expectation value, which is shown over here on the left. That is this unperturbed expectation value. So the zero over here means that it is with the average is with respect to the unperturbed Hamiltonian, and that unperturbed Hamiltonian only includes interactions between blocks. So, sorry, interactions within a block. It doesn't include the interactions between the different blocks. So that's going to be our perturbation. And so over here on the left panel, then the calculation of the effective Hamiltonian for the block spins then becomes the expectation value of e to the v times the partition function for the m blocks within the system, and that is just the partition function of one block raised to the mth power. And so we did that calculation last time, and we found that if Si is +1, we enumerated the four configurations, and we found that Z naught of k is 3 e to the minus k plus e to the 3k. And then I asked you to calculate this for S is -1. Did people do that? Yeah. Yep. One person did. Anybody else do it? Okay. What answer did you get?
Same thing.
Same thing. Same thing. Okay. Exactly the same thing. So over here then is our result up to now, and here is the Z naught of k, and so now we want to proceed with the calculation. So now let me show you how we do that, and so we're going to be. Pardon?
Can I ask it out before we proceed? I could ask a question.
Yes, of course.
Yeah, so why are we considering the interblocks interactions to be a perturbation when distance is not a parameter in our Hamiltonian? I don't see a parameter of distance, and I'm assuming that
there is a parameter because we're only nearest neighbors.
Yes, I'm just
so there are spins so most spins, their nearest neighbor is in the same block as them, and then they also have another neighbor which is in a different block.
Yeah, but why are we treating that as a perturbation? Is that smaller in magnitude than the intra-block interactions?
Because it seemed like a good idea at the time. Okay. I mean, if I can do the calculation of e to the v, expectation value of e to the v, the thing on the right-hand side, it's exact, right? Nothing to stop me doing it. So we're going to see in a minute to what extent this is a convergent perturbation series or something like that. Okay, so but in most of these things, it's experimental theoretical physics, meaning that during the early years of a normalization group, people just tried everything they could think of to see what would work and what would work well with a minimum of calculation. Okay. So it's a good question, but there is a distance here because we are looking at nearest neighbors. So it's not a obviously stupid thing. It's the nearest thing you can imagine, which is, I mean, remember in Kazanov's block spin picture, he just said by fiat, well, the interaction between blocks is the same as the interaction between the spins. Okay, this is obviously better than that. Okay, it's obviously something that we can improve systematically. Whether or not it converges quickly and is useful and so on, we'll have to see. Okay, so did I answer your question? Yep. Okay, so let's go on. So now what we're going to do, this is just to give you an anchor. This is described in section 9.6.3. We're going to do a perturbation theory. To get a renormalization group recursion relation. So I'm going to show you the basic idea, and it can be made much more formal and much more systematic. And I'm not going to do that. I'm going to do this just using high school algebra, just as a quick and dirty way to get the leading order term. Okay, so you can make this to arbitrary order using cumulant expansions and various tricks from probability theory and so on. We're not going to do that. So the thing that we have to calculate now is the expectation value of each of the v with respect to our unperturbed Hamiltonian. So that's the thing we want. And the basic method that we're going to use is we'll say, well, I'm going to do perturbation theory. Perturbation theory just says this is 1 plus v squared over 2 factorial plus dot, dot, dot. Okay, so that's the thing that we have to calculate. And so if I then expand that, so that is 1 plus the expectation value of v plus 1/2 the expectation value of v squared plus order v cubed. Okay, so that's what we're going to get, and here is our idea. The basic idea is the following. We're going to try to make this as simple as possible. And what do we ultimately want to do? Well, ultimately, what we'd like to do is we want to be able to read off the effective Hamiltonian. So the effective Hamiltonian, we have on the left-hand side, on the left-hand panel here, e to the h prime is z naught to the power m times the expectation value of e to the v. So the effective Hamiltonian appears as e to the effective Hamiltonian. So what we would really like is be able to write the expectation value of e to the v as e to the something. So the basic idea is if we write the expectation value of e to the v as e to the something or other, some stuff, then we can read off the effective Hamiltonian that we're looking for after we've done our coarse grading. And why can we read it off? Because then I've got e to the h prime is equal z naught to the k, z naught of k to the power m. Anything to the power m, I can write as e to the m log stuff. So that can be written as e to the something. And then if I can write the expectation value of e to the v as e to the something, then problem solved. So that's what we're going to do. So if we can write that, then we can read off a h prime. So here is our trick. So the trick we're going to do is we're going to say, if I have the logarithm of 1 plus x, then that is equal to x minus x squared over 2 plus a term of order x cubed. And what I'm going to do is I'm going to say, well, let's say that this thing over here, we're going to call that to be x. Okay. So if that thing is x, then if I write the logarithm of 1 plus x, so that now then is the expectation value of v plus 1/2 the expectation value of v squared minus 1/2 and then expectation value of v plus 1/2 v squared squared, okay, plus higher order terms. Okay, so we know that that's going to be true, and what we want is we're going to work to order v squared. Okay, so what that means is that when I write the logarithm of the expectation value of e to the v, so what that is going to be the expectation value of V plus 1/2 expectation value of V squared. But then there's another term which comes in from having this term squared. And so I'm going to get another term over here, which is minus 1/2 expectation value of V squared, like that. And all the other terms are higher order in V. So I'm going to neglect those. So we're going to write that as just this thing. That's the order V squared term. Then we have the order V term, and then the order V cubed term that we are going to ignore. And so then if the logarithm of e to the V is equal to this, then we can write down that the expectation value of e to the V is equal to e to the expectation value of V plus 1/2 the expectation value of V squared minus V squared. Like that, plus higher orders, which I'm going to neglect. And then this is great because now I can read off that this implies that H prime, the effective Hamiltonian for the block spins, is then going to be m times the logarithm of z naught of k. So that's the first term. And then the next term is the expectation value of v plus 1/2 the expectation value of v squared minus v squared. And then corrections. And so all we have to do now is evaluate these second moments. And these second moments are evaluated with respect to the unperturbed Hamiltonian. And so they will be functions of what the value of SI is. So notice here that on the left-hand side, I have SI, and all of these things in here, this, and this, these are all going to be functions and so that's how I'm going to be able to compute the effective Hamiltonian. So that's the trick. So now we just have to compute expectation of V and expectation of V squared. Okay, so let's now go ahead and do that. So any questions about the process before I proceed with the algebra? All right. So the next thing is the evaluation. So I'm going to write that V, since V is the sum of the interactions between blocks. So you can see it's written down over here on the left screen. So I can write V in the following way. I can write it as the sum over blocks I and J, but they're not equal to each other. Vij like that. And what is Vij? Let's have a look. So what you can see here, look on the left-hand side and look at the block spin I. So you can see spin 1 in block spin I and spin 2 in block spin I interact with spin 3 of block spin J. That's the only interaction. So I can write this then as K times S3J and then S1I plus S2I. Okay, so that's telling you what that interaction is. And then I have to average this over all possible I and J. And so that's how I will get what V is. Okay, so then the thing I want to compute next is I want to compute the expectation value of Vij. And so that's going to be just 2K times the expectation of S3 of J times S1I. And why is it 2? Well, because spin 1 of I and spin 2 of I interact exactly the same way with spin 3 of J. And so I'll just take one of them and just compute the number. Okay, so it's just that I get the factor of 2. Now, H naught, by construction, does not couple the blocks. So what that means is that therefore, when I compute S3J, S1I, where I and J are not the same, this then just becomes the expectation of S3J times the expectation of S1I, like so. So those things are decoupled. And now let's work out what this thing is. So if I want to compute the expectation value of one of these things, say S3J, so what that is going to be is 1 over the partition function of one block times the sum over the spin variables sigma j, and I only include configurations that are consistent with the value of Sj, and then I'm going to have S3J out here, and then in my exponential, I have e to the k S1J S2J plus S2J S3J plus S3J S1J. Okay, so I'm computing the expectation value of just the single, the third spin of block spin J with respect to the original unperturbed Hamiltonian. Okay, so now let's finish that. So if let's look at what possible values I could have. So I can have Sj is +1 or Sj is equal to -1. So now let's compute what S3J could be. So if Sj is +1, then what I'm going to get is the expectation value of S3J is going to be, so I put S3J, Sj is 1, so I now have to look at all the configurations of the sigmas that are consistent with Sj. So this is consistent with the value of Sj. So I choose it to be 1. So then this thing can be 1, blah blah blah. So you can compute that, and so when Sj, so there's let me just show you the configurations again. Where are they? Here. So when it's +1, so one of the spins here on the left hand side here are all the 4 configurations. Choose this one, the last one, to be S3. And so I'm summing over all possible values of S3. In 3 of those configurations, it is pointing up. In 1 of them, it is pointing down. So when I compute S3J, what I'm going to get is e to the 3k plus e to the minus k. That's going into the exponent. And then it's normalized by the partition function, which is e to the 3k plus 3 e to the minus k. So that's what I'm going to get for that expectation value. So all I've done is substitute in the values for Sj, and you can see that the numerator and the denominator are not the same because in 2 of those configurations, the value of S3 cancels out. And so that's why you get a different number of minus e to the minus k's in the numerator than the denominator. So you should check this, okay? It's just one line of algebra, but you want to make sure that you understand this. So after class, just go and check that. Okay. So then if I look at Sj is equal to -1, then S3J is then actually the negative of this. Okay, and you can check that too. if Sj is -1, yeah. All right, so that's the calculation of the expectation value of S3J. So therefore, I can summarize that by saying that the expectation value of S3J is equal to either plus or -1 times that thing, depending on the sign of Sj. So I can write that then as Sj times e to the -k plus e to the 3k divided by e to the 3k plus 3 e to the -k. So that's what S3J is, okay? So the next thing is, okay, well, what about the next term, which is S1I? Okay, so now we choose block spin I, and we choose the microscopic spin S1 in block spin I, and I bet you can guess what that's going to be. Somebody other than Ahmed, if you don't know. Anybody got any ideas? Without doing a calculation.
The same thing, but with SI instead of.
Same thing with except with SI, because we there was nothing special about block spin J or spin number 3 in block spin J. They're all equivalent. So you can say by inspection that this is going to be SI times exactly the same function. And you can check it by yourself if you wish, and you'll see that that's correct. Okay, so now we've done something really cool. Okay, and let's see why it's so cool. So that means then that if I compute, say, what expectation of V is, then this is then 2k phi of k squared times the sum over I and j being nearest neighbors, Si, Sj, and this function phi of k is equal to e to the 3k plus e to the -k over e to the 3k plus 3 e to the -k. Okay. And this k on the outside came from over here. What's that k over there? So our first, so if we just say, okay, we're going to just stop there. We're not, why do we need to compute the second order? We'll just compute the first order. We're happy with that. Okay, sure, go ahead and do it. So then what we've just learned then is that the effective Hamiltonian is equal to m log z naught of k, and then plus k prime sum over I and j, Si, Sj. K prime is now a new interaction. And what is K prime? K prime, we can just read it off, is 2k times the function phi of k squared. So that's our result. Now, is it correct? No, it's not correct because we didn't compute the order v squared terms. So there are still terms that we need to compute. So I'll write those as order v squared, and we're going to compute those now. But already at this order, we have now obtained our first non-trivial renormalization group result. And you can see that in this approximation, the result that we've got is exactly what Kadanoff guessed. Our effective Hamiltonian for the block spins looks exactly like the block spin like the original Hamiltonian with a renormalized coupling constant. So note this looks this is of the block spin Hamiltonian is of the same form as the microscopic Hamiltonian, but a renormalized coupling constant which we have computed. We didn't guess it. So this is all very good. It seems that this whole idea seems to be very productive, and so let's take a look and see what we get. Okay, so now the question is how good is this? And so the answer is let's calculate. And so this is section 9.6.4 in my book called Fixed Points and Critical Exponents. So now that we've computed our first renormalization group transformation, now we know what to do. We have a whole program that we have to do. First of all, we find the fixed points, then we linearize about that, then we look at the eigenvalues, then from those eigenvalues we compute the exponents. So let's do it. So step one of the RG pipeline, if you will. Okay, let's find the fixed points. So we have to solve K star equals 2 K star times phi of K star squared. So that's what we have to solve. So there's one solution. So there's one which is K star equals 0. There's another one which is K star equals infinity. And we expected those, right? Why do we expect those? Two phases. Okay. Those fixed points we know are going to correspond to the phases of the system. And we can already see what they are, because if K star equals naught, so that's J over KT equals 0, that's like a high temperature fixed point, T is infinity, or the nearest neighbor coupling J is equal to 0, so this describes the paramagnetic phase. And the K star equals infinity describes the ferromagnetic phase. So we saw that this actually came out. It wasn't just me telling you this is what's going to happen. If you could do the calculation, he saw it before your eyes with just high school algebra. Okay, and then there's another fixed point. So these are all the trivial fixed points. So these are trivial fixed points, and they're trivial, 0 and infinity, but they give you the phases of the system, phase diagram. They're not trivial in their implication, but they are trivial in terms of obtaining them. There's a non-trivial fixed point. So the non-trivial fixed point is we have to compute 1 is equal to 2 phi of K star squared, just cancelling out the K's. So if we have that, then that means that we need to solve phi of K star equals 1 over the square root of 2. And now you say, wait, what the heck? Phi of K is this disgusting function on the left-hand page. And now I've got to solve that as equal to 1 over root 2. So game over, just solve it numerically. Okay, well, no, you can actually work it out. Okay, so here's a trick. So now we have to solve for this. So now we do a trick. We just say, well, let x be defined to be e to the 4k. So if I do that, then from phi of k star equals 1 over the square root of 2, you can derive that k star equals 1/4 times the log of 1 plus 2 square root of 2. Okay, and you can work that out yourself. Okay, so again, check it. It's just algebra. So if you can't figure it out, it's not the end of the world. But it turns out in this particular case, you can work it out. And this is a number that's about 0.34 something like that. Okay, and K is equal to J over KBT, as we've seen before. So look, we've just calculated the critical temperature of the 2D Ising model. So let's see what we got. So we just got 0.34. That's what we just got. So what did Onsager get? So Kc from Onsager. So he calculated that, and what he found from his exact solution is it's 1/4 log 3. Okay, that's what it turns out to be, which is 0.27, something like that. So not bad, right? Onsager did this stuff that really makes your brain explode, and we just did high school algebra, and we got an answer that's not bad and definitely better than what you would get if you did mean field theory. All right, so that's great. So we're on a roll here. So now let's compute the critical experiments. So I should say this is step. This is a step. Step 1, step 2. I don't know. Step 3. Critical exponents. So what we're supposed to do is we're supposed to say, well, lambda t, that critical exponent, is dk prime by dk evaluated at k star. So you differentiate our formula, you plug in the value of k star, and I'm not going to go through the algebra for that, you can all do that. And if you do that, what you end up with is 1.62, something like that, okay? And if you say, well, what did Onsager get? So lambda t from Onsager, well, we calculated that last time. Remember last lecture, we worked that out. I don't know if I can find it here quickly. Hopefully I can. Yeah, so lambda t from Onsager, that's over here on the left-hand panel, and that is equal to the square root of 3. And so that's the square root of 3. Square root of 3 is 1.73, something or other, blah, 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 and then what goes on after that. And so that's not bad. So that's not bad. And it's even more amazing because we only worked to the lowest order. To order V. So now let's try to improve it. Improve by going to order V squared. So okay, so order V squared. So this is going to be a bit messy, but it's not too bad. So what we're supposed to compute then is the expectation value of V squared minus the expectation value of V all squared, like that. So let's write that thing out. So this thing is going to be a bit messy, and I guarantee you probably won't get every single step of the calculation as I go through it, because there's certain terms that you have to see. This one is this one, this one is this one, and this one cancels and stuff like that. I'll do my best, but it's you need to work through it yourself to really see how it works. So this is going to look like this. It's going to be k squared. And the expectation value, I'm going to sum over I and j, another sum over m and n, and then si, sj, sm, sn. So it's going to be that minus, and then this thing we just calculated squared, which is going to be the sum over I and j, the sum over m and n, and then si, sj times sm, sn. And so that's what it is. Now, I need to tell you what those things are. So let's have a look at the picture again. So let me draw this over here. So here's my block spin, Si. This is Sj. And then in this picture here, I'm going to think of this as being Si, this as being Sm, this as being Sn, and this as being Sj. Okay. So what the point about this is that in this picture here, and then there's this interaction like that. In this, the point is that in these two equations above here, I and j are on different blocks. And m and n are on different blocks. So I didn't complicate it by putting in the block labels as well, but the m and n are in different blocks and I and j are in different blocks. Okay, so that's important from this picture. So now we've got a little bit of combinatorics to do. So so now when we look at this term here, this term SI, so that is going to be SI 0, SJ 0. They're in the same block. No, they're in different blocks, and therefore they're uncorrelated. And so that thing is going to be 0 unless SI is in the same block. Wait a minute. Yeah, I've got this right. Unless SI is in the same block as SM, or the other way around. So basically, you can work out which of these terms will be 0 or non-zero, depending on where the I and J's and M's and N's are, and that way you can get what the result is. Now, what I'm not going to show you is that well, I'm not going to go through the detailed calculation, but it's in my book. One of the things I want to point out to you is this: I now have an interaction between this spin and this spin going through here, through here, through here. Okay, through these different blocks. So now we've generated second and third nearest neighbor interactions. And to you really have to go through that in order to really see that. I'm not going to use the class time to do that. Okay, so if you feel motivated, go ahead and do the calculation yourself. I want to just tell you what the result is. So when you work it out, here's what you get. So the first thing is we're computing, we're ignoring H at the moment. So now we've got two interactions we have to worry about. One is lambda t, the same interaction that we've had before. And that turns out now to be 1.77 if you compute it. Okay. But we've also generated new interactions, second nearest neighbor interactions, third nearest neighbor interactions. And so they have corresponding renormalization group eigenvalues. So lambda 2 and lambda 3. And this one turns out to be 0.23, and this one turns out to be minus 0.12. Okay. All right. What can you tell me? What does this calculation reveal? What does this imply about second and third nearest neighbor interactions? What does it tell you? Not even. Okay, let me try to help you with the answer. So what we saw in our general renormalization group formalism was that we have a whole bunch of coupling constants evaluated at a particular fixed point, and we saw that we could classify them into relevant variables, irrelevant variables, and marginal variables. Okay, so what I'm asking you is, does the result of this calculation I'm showing you say anything about that classification? What is the condition for relevant variables?
Lambda should be, I mean, the mod value lambda should be greater than 1.
The modulus should be greater than 1 because they're equal to L to some exponent. And one of them is greater than 1, that's lambda t. So we know that this one over here is relevant at this fixed point, as we expect. Okay? What about the other two? They're irrelevant, yeah. These two are irrelevant. We still had to calculate them in order to be able to do the calculation to get the result for the relevant variable at order v squared. We had to work out all these other terms here, which I spared you the detailed algebra. We still had to go through to do that in order to be able to compute the derivatives and compute the value of the fixed points and work it all out, but they're irrelevant variables. So let's just summarize what this tells us then. So if lambda is less than 1, which it is for lambda 2, lambda 3, then they're irrelevant. But these couplings, these irrelevant couplings, are generated by our real space renormalization group. That's what we call this, in order to get an accurate estimate of the relevant eigenvalues. And let's just remind ourselves what they were. So lambda t for Onsager is the square root of 3, which is 1.73, blah, blah, blah. When we did our first order calculation, and we call that lambda t1, then we got 1.62. And now when we did our second order calculation with a lot more work, and I spared you the agony of going through it, we got 1.77. And so that looks very good. So we're pretty happy, particularly since I did the work, not you. Um, but anyway, so that looks all very good. Now we know that there are another relevant variable that we have to worry about, and that's the external magnetic field one. So let's go ahead and work that out. And although in principle it's a bit of a messy calculation, there's a dirty trick that we can use to calculate that very easily. So the next thing I want to do is calculate the magnetic field eigenvalue. And we know we have to do that because we know that there are two variables that we tune in the lab in order to get to the critical point. We tune the temperature to Tc, we tune the external magnetic fields to H equals 0. So we know there's another relevant variable that we have to worry about, which is lambda H. So for that then, we need then to set H to be non-zero. And if we do that, then we can compute lambda H. So we know what it is from Onzaga. I showed it to you last time. I'm sure I've got it in my notes here to reproduce in due course. So let's now see what the trick is. So the trick, we're going to use a bit of knowledge to help us do this in a very quick way. So here's my trick. We know by up-down symmetry, by time reversal symmetry, that the critical point is going to be at H star equals 0. And so that means that if I take delta H to be H minus H star, then H star itself is equal to 0 for delta H. Okay, so now let's ask what happens when we introduce the external magnetic field into the Hamiltonian. So now the calculation of the block spin Hamiltonian is going to be like this. We start off with our Hamiltonian e to the h prime. That's the thing that we already calculated. We're going to now say we're going to switch on a small magnetic field. We're going to consider that to be a perturbation, and so that is going to add a perturbation to that effective Hamiltonian, which we want to compute what it is. Okay, and then in the microscopic Hamiltonian, well, I've got the microscopic Hamiltonian. It is the original one that we just used, plus the perturbed version, and we're going to sum, as we did before, over the microscopic degrees of freedom within the block spins. So we're going to write it like that. And what is this delta H? This delta H that is here in the microscopic Hamiltonian, well, that delta H is just H times the sum over I SI. Right? We're just looking at the external field coupling to the spins, and I can write this as delta H times the sum over I SI. And if I'm summing over all the spins in the system, I can write that as delta little h. I can sum over all the spins in the system by first of all summing over the block spins, and then summing over the spins within each block. So that would be SI, capital I, like so. So then if I want to compute what delta H prime is, then delta H prime is going to, by definition, be the transformed delta H times the sum over I of SI. That is by definition what it is going to look like. And that is going to be then the sum over the microscopic spins of e to the h times delta h, and then normalized by the partition function. And so that means that I can write this as the expectation value of delta h times the sum over I the sum over all the spins in I, Si, I, like that. And just continuing that equation, well, that is nothing more than saying I have delta H on the outside times the expectation value of the sum over I, and then S1I plus S2I plus S3I, the spins within the block I. And this thing over here, we already calculated this. Okay, we remember we already calculated SI with respect to Hamiltonian zero. We already calculated. And that thing is equal to SI times times phi k. That was the thing that we calculated 15, 20 minutes ago. So then we can just simply read off the renormalization group flow equation for the effective external magnetic field. That then is going to be 3 times phi of k times delta H. And why is it 3? Well, it's 3 because there's 1 for each of these terms inside the block spin. All right, so that's the recursion relation. At least I didn't do it as fully systematically as I did before. I just showed you a quick and dirty way to get to that using, knowing how to do it. And so once I know that, then I can compute the renormalization group eigenvalue.
Should be capital H by delta capital H. Hamiltonian.
No, it's the recursion relation. Oh, no, it's not, because it's the recursion. It's this thing on the left-hand side. It's the recursion relation for the transformed delta
It's
H.
renormalized, like you're just renaming things.
So you look over here. No, look over here. So I'm doing this, and then that by definition is equal to that. And so from this, then I can read off what is the delta H price. Does that answer your question?
Yes.
Okay, so then we have that. So now I have to just differentiate. So lambda H is equal to 3 phi at K star, and that is 3 over the square root of 2. Because remember, phi of K star, the non-trivial fixed point, had the value 1 over square root of 2. So 3 times that is just 1 over root 2. And that is equal to 2.12. And then last lecture, I showed you what the exact answer is by working backwards from Onsager's solution. And so that we got as 2.8. So we didn't do bad. We got a pretty good result for the critical behavior. And we got the critical exponents to reasonable accuracy with a very modest amount of work. And more work than doing mean field theory, far less work than doing Feynman diagrams and so on. And I did some of the work for you, so you don't have to see it, but it's not, the summary is that it works. Summary, we have a systematic way systematic but laborious to compute critical behavior. And it gives you reasonable results for a very difficult problem. Okay, so let me decide what I want to do next. I think what I'm going to show you next is the phase diagram. Wait, that wasn't what I wanted to have happen. What happened here? Nope. Try again. Okay. 179, 180. All right, so let's have a look at the flow diagram. So I'm going to draw the axes like this. So here is K and here is H. We know that there is a fixed point that we've calculated at the origin, which is our paramagnetic fixed point. We know that there's a fixed point. Let me call it, let me put it over here. It's meant to be at infinity. So this is the ferromagnetic fixed point. This is the paramagnetic one. We saw that there is a non-trivial critical fixed point over here. So this is the critical fixed point. We saw that the renormalization group recursion relation for delta H is it increases because you have this positive eigenvalue. So we know that there are flows that go like this, and of course they also go to negative like so. We know that the critical fixed point is a repulsive fixed point on the H equals 0 axis. So the flow goes like this. So it looks like that. And in the vertical direction, it's not obvious. I'll try to explain a little bit what that's going to look like. Well, it looks like this. We know that the flows along in the H direction are going to go off to infinity. So what's going to happen is by continuity, the flows like in this direction are going to go off like this. So if I start slightly off the critical fixed point, I'm going to go off like that. Similarly, if I start here, slightly above K star, I'm going to go off like this, but eventually I'm going to flow like so. So my flows sort of do something like this, and depending on how close I start to the manifold, I'll do something like that. So the topology of the flows is going to look something like that. So let me just put the caption in. So C is the critical fixed point. P is the paramagnetic. F is the ferromagnetic. And this one is stable. This one is stable. This one is unstable. And when H is non-zero, that means we flow to plus or minus infinity for H. Okay, let me tell you now what are the renormalization group eigenvalues for the trivial fixed points. So let's write down the RG eigenvalues for the trivial fixed points. So you probably believe that this flow diagram looks right because you already saw that in H, it'll flow up or flow down. The critical fixed point you know is unstable, so you can probably sort of just fill in. But let's just have a look at the real calculation. So let's look at the paramagnetic fixed point. So now we know that K star for that one is equal to 0. So we plug that in, and what we get is that the lambda t is equal to 1/2, and lambda h is equal to 3/2. Okay, so these are the renormalization group eigenvalues. But remember that the renormalization group eigenvalues, what is relevant and what is irrelevant, etc., depends upon which fixed point you're talking about. We're talking about the paramagnetic fixed point. So you can see the lambda t, which was positive at the critical fixed point, is smaller than 1 at the paramagnetic fixed point. And so it is stable, but it's unstable in the h direction. So this is, it's stable in the k direction, but unstable in the h direction. So that's the paramagnetic fixed point. If I look at the ferromagnetic fixed point, so that's the one is infinity. So then what you find is that lambda t is equal to 2, and lambda h is equal to 3. Okay, so you might be a bit puzzled by that. Why might you be puzzled by that? Gregory?
Because flows along the k direction go towards the ferromagnetic fixed point, but we see that the eigenvalue is greater than 1. So
Right. So it's a bit weird.
Yeah.
Right. Okay, so
Ferromagnets in real life.
say it again.
Also, we see ferromagnets in real life. That should be a stable.
Yeah, and the flows I've drawn. So you're both right. So the comment is F. We expect it to be a stable fixed point, and so then we would expect that lambda t should be less than 1, but it's 2. So what the heck? And so the answer is it's really the answer is it's really an artifact of being at infinity. So so the reason is this: if you're at infinity, nothing can get bigger than infinity. Okay, it's like Buzz Lightyear, right? To infinity and beyond. Okay, you can't do that. So what you have to do is the solution is write the recursion relation in terms of 1 over k. Okay, and then you've got a chance to get both answers. So then in terms of 1 over k, it goes as k to the minus 1 is equal to 1/2 of k to the minus 1. This is prime. And so that means that k to the minus 1 equals 0 is an attractive fixed point. And that means that k prime is greater than k. So basically it just pushes to infinity. Of course, it can never get there. And so that's what's going on there. So that's comment number 1. Comment number 2. I want you to look at the value of lambda h at the ferromagnetic fixed point. Okay, So what I told you when you do the calculation, and I invite you to check it, the value of that is lambda h is equal to 3. Okay, so you say, okay, 3, so what? Well, I want you to remember that lambda h is equal to not lambda h. I want to remind you that the renormalization group transformation, our RG transformation, has the block spin size being the square root of 3. And so what that means is that lambda h is equal to the square root of 3 squared. In other words, it equals L to the power D, and remember, D is equal to 2. So our magnetic eigenvalue goes like L to the D, and I told you that that was a signature of a discontinuity fixed point. So it means that it's discontinuity fixed point in the way that the magnetization varies in the H direction. And so what that tells you then is that for any temperature less than Tc, it flows to the ferromagnetic fixed point, and that has a discontinuity. And so if I now draw the phase diagram, it says that the phase diagram that I'm predicting looks like this. Now I'm going to write it in language of H and T, the physical variables. So what we found is that there is a Tc, and then we found that for T less than Tc, if I start at any T less than Tc, I flow to this ferromagnetic fixed point over here. And that ferromagnetic fixed point, its basin of attraction is a discontinuity fixed point. So the discontinuity is then that there is a discontinuity across here. And that means that for any starting point, T less than Tc, I will have a discontinuity in the magnetic field direction. And that makes perfect sense because we know that the physical picture of the system is when I'm up here, the spins are mostly pointing up. When I'm down here, the spins are mostly pointing down. And so we can see that the magnetization changes discontinuously across H equals 0 and T less than Tc. And I didn't show it to you in class, but if you want to see how this is worked out, look at section 9.7 in my book, and that explains the discontinuity fixed points. A lot of people don't know about that. Most people think that the normalization group only tells you about critical exponents, critical scaling functions, critical points, and so on. But it's not true. You can get first order phase transitions. You can learn everything you want to know about the system from the normalization group, not just the critical behavior. It's just that for critical behavior, it's the only way to do it. There's no other way to do it, at least analytically. Okay, so that is where, well, let's see, it's 1:47, so we've got 3 minutes left. Let me just give you a preview of what we're going to do next. So I think this is basically finish for today. Next time. So next time, what I want to show you, next time I'm going to show you a trick method to factorize, to do statistical mechanics using a different formalism called the transfer matrix. And in the homework that you did already, you did a calculation like that. Remember in homework 2, you were able to solve exactly the one-dimensional model by adding terms to the end of it and then making a recursion relation for the partition function in the homework. Yes, you did it. Most of you, all of you, in homework 2, right? We're going to generalize that in general. So I'm going to show you. So the next time we're going to find a method we're going to develop a systematic method to do the nearest thing we can do to make the partition function factorizable. So we already know that because it has interactions, it cannot be factorized. So then you can ask, how close can we get to factorization? And we can't get to literal factorization, but if we map it into a kind of matrix problem, then we can get to something that is as close as you can get to factorization. And that's what we're going to show you next time. And why is that important? This is the way that Onsager used to solve the 2D Ising model. He did a super sophisticated calculation. We're not going to do that. We're not going to do anything like that. But this method of factorizing it is the thing that you need to do in order to be able to do systematically calculations in statistical mechanics. And also it's important because when you think about, there's a mapping between statistical mechanics and quantum field theory. Those of you who end up doing field theory, doing theory, it turns out that anything that you do in quantum field theory can be regarded as basically a statistical mechanics problem in a slightly different dimension. And this way of doing things in statistical mechanics is the closest thing to the Feynman path integral in quantum mechanics, and shows you how you can do that. So for most of you, you probably won't need to know it, but it's not that hard. It's not this hard to do. It's really quite beautiful how it works. And so I want to show you that, and I will give you a a homework set that I know you're not going to do. A fourth homework set that is 100% optional, will not count to any final grade, just for something that those of you who want to do later on can do. And you'll have some exercises in using this formalism. So this is another way to do a renormalization group. So I'm going to show you that next time, and then we're going to go to the well, I think I'm going to show it to you next time, and then I'm going to show you. I'm going to do it fairly quickly, and then I'm going to show you the next topic, which will be the dimensional analysis and the sort of introduction to a field theoretic way to do renormalization group. So the thing you've learned today is you can do real space renormalization group, but it's a lot of work. So it turns out with a little bit more intellectual effort, one can then find a tool that is much more economical and easier to calculate, which is surprisingly, you might think, to hear me say this, it turns out to be a sort of field theoretic calculation. I'm going to show you a little bit about how to do that. We're not expecting mastery in this class, just so that you at least get exposed to it, so you've seen it before. Okay, so that's where we'll end. Let me just say this. Everyone here is taking the class of credit submitted an abstract to me. Anybody not? And everybody who sent me one got my response back. True? You didn't? Oh, man. Okay. Then, okay. Anybody else not get one? You didn't either? Okay. Can you send me a message in Teams just to remind me? And when I get back to my office, I will find it. So I know one other one went into my spam folder. And I eventually had to find it. So send it to me again, and or at least tell me that, remind me that to look for it, and I will dig it out and find it and then give you the comments.
Would you
Okay.
prefer if we sent it directly on Teams? Would that be easier?
No, send it to me in email so I've got a record of it and so on. It's just that, you know. Okay, so I'll find it. If I don't find it, then I'll ask you to send it to me in team. I don't want to inconvenience you, but I want to but make sure that I have got that back to you. Okay, so two didn't get the responses. Okay, that's the end of today's lecture. I'm going to stop the recording and we should leave, and then I will talk to you after, answer questions outside.